Oop. I'll begin with a word of prayer. Here we go. Dear Father, we thank you for this day, and just ask you to bless this class. Help us to glorify you in what we do, and just to understand what we need to about the material today, Lord. In your name I pray, Lord Jesus. Amen. So, thank you for your homeworks. I hope. Let's see here. So, we'll look at the solutions to these, since they're probably fresh on your mind. So problem 1, hopefully is pretty straightforward here. Just basically separate and integrate. I mean, you do need to know the law of exponents, and the definition of cosh is 1/2 e to the x plus e to the minus x. So once you use that, we're just looking at exponentials, and there it goes. Now there is of course a way to write this answer in terms of cosh and sinh as well, and if you did that, that's also fine, assuming you did it right. Let's see here. Problem 2, again, is separation of variables. This one's a little bit more fun because the integration involves partial fractions for the x, right? So here's your calculus 2. So that brings us to here. There's a 5th out front. This guy over here, you make a u equals y plus 2 substitution. That brings us to an inverse tangent integral, just like that. And then I just said solve, right? So like this would be a legit solution. If I said explicitly solve, then you'd need to put what's in the box. I'm not, you know, I could have boxed this and that. Don't like read too much into what's boxed here, all right? I've talked about this before. I'm talking about it again. So if I asked for an explicit solution, you have to solve for y. If I don't, you don't. But I thought I'd just go ahead and solve for y since it's not too hard here. Now this right here, I'm simplifying. What am I doing? So the difference of two natural logs is the natural log of the quotient, right? And then I've got a 1/5 multiplying it. When you bring 1/5 inside, it becomes the 1/5 power. So you could do that. Now if you didn't do that, again, I wouldn't take points off. Do I have any paper? Well, I don't know, Benjamin. I don't think I do, actually.
I have paper.
Oh, there you go. Careful your head. Watch the corner there. So next up here. That's okay. So next up here, we have this differential equation, and so I look at it, and it's fairly apparent that like separation of variables is not going to work. It's nonlinear, so it's not integrating factor method, right? So yeah. So I basically I said, okay, well, I want to have partial f partial x equal to the the coefficient of dx, right? And I also want partial f partial y to be this, the coefficient of dy. So I integrate the x coefficient, which took a little bit of work. Uh-oh.
Nothing happening.
Yeah. Okay. So yes, so we integrate with respect to x, and y integrates to xy, inverse sine after a little bit of integration by parts, integrates to that, standard Calc 2 stuff. And so we got this plus this, and then a constant. Now I plug that into here, and it gives me this equation, and then the x's, they cancel. So we're left with dc1 dy is this, which integrates to inverse tangent of y, and then I put it all together. Something I should emphasize here is if you were to take this box and shift it over ever so slightly and just say f equals to that, that's lovely, but I will take points off because that is not the solution. We're looking for a function or a graph which solves the differential equation. This does not do that. But what's in the box does, this collection of all x and y that solve this equation, that is a solution. That's a curve whose differential consequence is the differential equation. So this is a common confusion because you guys confuse the algorithm with the logic, right? Which the algorithm is, you need to find the big F, right? But that's not the end of the story. Uh-oh, paper dagger fingers. That'll happen. So it's okay, I've got armor on. So yeah. You guys know what I'm saying? Am I just saying words that don't mean anything to you? Yes. Well then, watch it back later. What? Are you?
See what I'm making?
It's too late. I already. Is that you're doing Gollum now? I don't understand the I don't understand the relevance, but okay. So next up, we're trying to find a Cartesian equation, which is parametrized by the solution of that following system of differential equations, right? So what I'm after here is I want to find a Cartesian solution, right? So if you want to find a Cartesian solution, a nice trick to use is to eliminate time at the level of calculus, right? So dy dx I can write as dy dt times dx dt. I should wear glasses. So I do that, and then separation of variables, right? Yay! That wasn't bad, was it? I hope it wasn't bad. Now, the wording I use in this problem, it's a little cagey, right? Find the Cartesian equation, which is parametrized by the solution to the following system of differential equations. So I thought, in addition to what's asked in this problem, it might be interesting if I actually just solved the system directly and showed you that it worked, right? So that's what I do next. This was not part of the solution, it's just, extra. But we know how to do this now, right? Because we know the complex eigenvector method, so we could solve it. And so I do that. We get eigenvalues plus or minus root I, and I look at this, and from this I extract this complex eigenvector, right? Then I write down the complex eigensolution down here. Come on. Oh, man. Come on.
Father, look what I found.
Oh, you found my markers. That's wonderful. Okay, just don't write on the wall. Let's see here. Not in this class, anyway. When we get to physics, you can write on the wall. So they got papers up in there. I've been thinking about adding things to them. But anyway, so here's the complex eigensolution. So this, remember, is cosine plus I sine, right? And this vector expands into the real part plus I times the imaginary part. I multiply it out. I have a real part. I have an imaginary part, which I separately take as solutions. And so there you go. That's the solution. Now, it's not readily apparent, I suppose, what's boxed at the bottom of this page here, right? Is it clear to you that if I plug this and that into that equation, that it works out to give you a constant? I mean, it's not obvious to me, and I didn't really want to do the algebra, so I used trigonometry instead to rewrite my solution as a magnitude times sine of a shifted phase angle, and then my y would be that, and then it's pretty obvious if you plug those in, they work. All right, so there you go. I have shown my claim was true. The solution of dy dx equal to 2x over minus y is in fact parameterized by the solution of that system, right? I did not expect you to solve the system because this problem was early on in the homework when we didn't know how to find complex eigenvectors and all that, right? So hopefully my homework is usually more or less in order. Let's see here. Next up, you're supposed to find a level curve which serves as integral curve of f. So this is basically the same math as the last one. We want to line up dx dt to be p and dy dt to be q. So we can eliminate time by looking at dy dt divided by dx dt, which gives us q over p. Something wonderful happens here because that messy, ugly denominator just poof, it's gone, right? And then we can separate, we can integrate. But then, of course, we have to, fit that initial data point of x naught, y naught, which is a little bit troublesome. Come on, come down. So I do that next. I plug in the point. I find out that c has to be a particular thing. And I found this somewhat ugly solution, right? And then what I thought is, I can clean this up. I can do better. So I multiplied it by 2. And I completed the square, and it gave me this. So you have a circle that's centered at 1, 0 with this radius the square root of that, whatever that is. Hello. It's a good thing. It's a good thing it's a good thing I wasn't taping that. Yeah. It could be embarrassing. So I don't want to spend too much class time on this. Basically, all that goes on here is I use the rules of the exterior derivative that I introduced in class, and ultimately this is 0 because eventually we get to partial derivatives commuting, right? And the minus comes because I have to swap the dx dy to dy dx somewhere, which gives us a minus. And that's pretty much it. In terms of vector calculus, if you use the identities we worked out in class, we worked out that the differential of a function is the work form of the gradient vector field. And we worked out that the differential of a work form is the curl of the vector field which underlies the work form, which means that this is the flux form of the curl of the gradient. And so in other words, d squared equal to 0 shows you that the curl of the gradient is 0, which is a, well, I would say well-known vector identity from vector calculus, but that's probably a little bit wishful thinking on my part. Now, this next problem I made a typo in, which means some of you will have crossed out the 3, others of you will have crossed out the z cubed, depending on when I talk to you, because I changed my mind. So sorry. So if you did anything here that is logically consistent, you will be fine. All right? And the long story short of it is that when you take the exterior derivative of the work form, you get something that's non-zero, and that corresponds to the curl of the gradient. That means that we can't have this is equal to, the work form of a gradient vector field. Because if we did, that would be a problem because this should be 0, but it's obviously not. So anyway, this is another way of saying that this calculation basically shows that the curl of the vector field is not 0. And you might recall from calculus 3 that if the curl of the vector field is non-zero, it's not conservative, right? So anyway, that's all that was. All right, so back to the major subject matter here. Find the explicit solution of that. So again, separation of variables, right? But notice that the algebra leads us to plus or minus that, right? But it's not up for grabs. We must choose the minus, otherwise we can't fit. Careful, Benjamin. You're gonna, if you hit your head on that corner, it's not going to be a good day. So minus has to match minus, which ends up giving me this is my solution, right? So some of you, when I had the quiz problem, you're still putting plus. This is early on when this quiz happened, right? Pretty early. So you were still putting plus minus. Some of you ignored the minus issue altogether. There were a variety of errors. But you can't put plus or minus here because the plus is wrong. All right, you must make a choice. Now, if the question was find the general solution, if I didn't give you, if I said find the general explicit solution, right? The general explicit solution, I didn't give you information about whether you're going through a positive or negative point. This is the general explicit solution. You do have to include the plus and the minus because those are possibilities. But not for our data, if that makes sense. Problem 9. If you guys have a particular question that's vexing you and you want me to jump ahead, feel free to jump in, all right? Otherwise, I'm just going to keep plowing through here, see where we get to. Problem number 9, because I wanted to make sure that there's time. Part of the reason I'm making this homework due today is so that there's a little bit of daylight between when your homework is due and when the test happens. Because many of you are just learning of the difficulty of doing these problems in the last 48 hours or so. So I want there to be another 72 hours at least before you take the test, right? Yeah. And the test is when? Wednesday. Okay, good. I hope you were going to tell me Monday. That would be embarrassing.
No, it's Friday, right?
You want to make it today?
No.
I mean, I can go print it out. So hopefully by Wednesday you can understand whatever it is you haven't understood here, and perhaps a little bit more. Okay, so because I do think there's a certain weakness of this homework. So there's something that's kind of missing a little bit, so I'll talk about that as we go on. But okay, anyway, so that's partly addressed by the quiz, which you guys are working on, right? Which is due Monday. So which should take considerably less time than this. The quiz is in Canvas. I haven't handed it out in here.
Is the quiz like open notes at all? Or
You can work together. It's open notes, yeah. So I say quiz somewhat loosely, like an online quiz.
Okay.
So, I'm sorry, people would never work together on online quizzes. What am I talking about? That's crazy. I mean, we proctored them after all, right? Oh, that's right. Never mind. Let's see here. So this one here, again, I'm trying to find the integral curves. So I'm back to the problem. I want, I want dy dt to be the q part, and I want dx dt to be the p part. So if I eliminate time at the level of the calculus, that gives me dy dx is q over p. All right. So if you think about this, in terms of geometry, there's a few problems that we've looked at. And the one is finding integral curves of a vector field. I've focused a fair amount on that in this semester. But we also talked about finding orthogonal trajectories to a given curve, right? So you need to be ready for both of those questions, right? And logically speaking, you ought to be able to answer other questions which are a little bit different. Like, what if I asked you to find a set of curves whose slopes were always twice the slope of the given set of curves? What would you do? I see I shouldn't have given you that stapler. It's made you more powerful than I could have expected. So you would set, if you were given dy dx equal to f, and you wanted to find the double slope curves, you'd solve dy dx equal to 2f, right? That's it. So orthogonal trajectories, we solve -1 over f because that gives us slopes which are perpendicular to the given set of slopes, right? So I don't know what that means, but so you have the baseball cards. What if those baseball cards are worth a lot of money? They might be worth like a whole 30 cents or something, you know? All right, so anyway, getting back on track here. After we write that down, we've got a what? What is this? So that's another thing that you need to have on your list of things you need to learn, which is what kind of enemy are you facing, right? Is this a separation of variables problem? Is this an exact equation? What is it, you know? And so if you look at this, see what I said? You're lucky it's just your shoulder. All right, go sit over there. Come on. Do you want to come to my other classes?
Yes.
All right, then behave. So there's a nonlinearity in x, right? But that's the independent variable. So the dependent variable and its derivative both appear linearly. That makes this a linear differential equation. And as such, I can rewrite it in standard form, like so. And then I can recognize, integrating factor method. So I need the exponential of the integral of this guy, which works out to x squared. I multiply the differential equation by x squared, reverse product rule this thing, integrate both sides, and solve for y. Although I didn't actually say, oh yes I did, answer it explicitly in terms of y as a function of x. So I made you solve for y here without question. You guys any questions so far? So to recap, for first order problems, what are our methods? Separation of variables, exact equations, integrating factor method, right? And what's the other thing that's out there? Substitution, right? So I don't think there's a Bernoulli problem in this homework, which is unfortunate. That is part of the material. We had a class. So like as you're studying, there's at least 3 things you should look at, right? Which are this team mission, obviously. Quizzes I've given in class or out of class, right? And then examples that we've done in class. Those are the 3 main sources I draw on for problems. Okay, what is it?
Just a solution for number 10.
Yeah. Yes, Jordan.
Could we jump to, so
Yeah, we can jump to 17. I'll finish this. So this is the substitution problem. For a substitution, I will actually suggest the substitution, but then you got to work it out, right? So a substitution, much like for when you use substitution in Calc 2, what you have to do, there's two things you have to do, right? You have to change the integrand and the measure, right? It's not just enough to do the whatever you're integrating and ignore the dx. You have to change the dx to the du. And the same thing here. You have to change both the expression and the derivative. So usually I will just differentiate what the substitution rule is and then solve for dy dx and then plug it in over there. And then, anyway, this is actually separation of variables, so it wasn't that bad. And don't forget, with a substitution problem, you do want to change the answer back to the form, you know, in terms of y and x, right? It may or may not be able to possible to solve for y, but you do want to change back to the form y and x. Not ignoring you, Jordan. Let me finish this one here. So this one here, you want to make it exact, right? So that means that your coefficients m and n must solve the closed condition, right? Because that's a necessary consequence for exactness. You need that the y derivative of the thing matching next to dx is equal to the x derivative of the coefficient of dy, which here amounts to giving me this equation. Of course, these just gone. And then we have to set this equal to this. Now, maybe you haven't solved many equations like this in your life, but search your heart. And you can see that b is 2, and y must be, excuse me, yeah, and a must be 1 in order to match that up, right? If you want to know, like, what's a method to derive that, I suppose you could take a partial derivative of this with respect to x, and then you'd get, you know, this is equal to 2y, and that would force the, like, b times y to the, you know, b minus 1 to be. Anyway, you could, like, if you wanted to, you could do that. But you can really just match powers when you have something like this, all right? You guys don't care about the derivation of that, I don't think, anyway. Now here, to solve this exact equation, I am showing you my actual method. So sometimes I write a lot of stuff down, I integrate one, I plug it into the other, I write a bunch of stuff. But the truth is, under time pressure, what I do is guess. So I take this and I integrate with respect to x. I've got x squared over 2, y squared. That's this term. This integrates to xy cubed, right? This integrates to e to the x. Great. That takes care of this. I integrate this with respect to y. I get 1/2 x squared y squared. Oh, I already got that. I don't need it. I integrate this with respect to y. I got, xy cubed. Don't need it. Already got it. Nothing to write down there. I get to this. I integrate cosine. Sine. So I put that down. Done. See, because I know that then the differential of whatever I write here is that. And that's how I check it. I say, if I take the differential of this, do I get back to here? Well, yeah, I do. So that's the level function. We can make it more complicated if you'd like, but that's really it. Right? It's more complicated when some evil professor does something like throw an inverse sine in there. Integrate that. You know, stuff like that. But if the integrals are easy, whoa. You should be able to write them down. Okay. 17, you said, Jordan, right? All right. So let's see here.
Is this going to be posted on Canvas?
Oh yeah. It's not yet, but it will be. Do 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 do. All right, come on, come on. All right. Oh. Oh right. Oh, no, this is not a Bernoulli problem, is it? No. So here, this is make a v equals y over x substitution. I guess I haven't told you explicitly make v equals to y over x. So if you saw this, I guess technically, since I've told you what I've told you, if I had this on the test, I am obligated to also try v equals y over x here, okay? If I'm going to be true to my claims. Okay. So when we do the algebra, we get y squared over x squared plus 2y over x, which is v squared plus 2v, I believe. And on the flip side, so when I see something like v equals y over x, I don't differentiate that, because why? Why would you do that? Like, it's just ugly, right? So multiply by x first, then differentiate. It makes it easier. And also it gives me dy dx directly, which is what I'm after. So if dy dx is v plus x dv dx, which I can plug in for dy dx. Again, we have to change the the differential equation and the derivative involved. So we have this and that, and then separate and integrate. There's some partial fractions to do here, right? Which you know from Calc 2. It shouldn't be too much of a trouble to do partial fractions. And so I do that. And I had a thought here, which was to make my life easier, I should bring x to the other side. So if I subtract, think about this, if I subtract the natural log to the other side, that has the effect of dividing the quotient by x. Right? Stuff minus natural log of stuff is stuff divided by stuff subtracted inside the log. So bringing this to the other side divides by x, but x times v is y. And so that's kind of nice, because I get y over x is divided by y plus x is equal to that constant after I exponentiate the equation, which gives me this solution. Now that I have worked this out differently in different semesters previous. And so like a past semester I worked this out, I ended up with a solution that looked more like k x absolute value of x divided by 1 minus k times absolute value of x. This is how it looked for me in another semester. All right, so it might look a little bit different for you too in this problem. And this is not posted on my website, but I will post also the solution to my 2018 quiz 1 for you guys, since it has a lot of the same problems. And when I worked them in 2018, some of them I worked a little bit different, and I don't know, it might be helpful to you to see me work some of these problems a slightly different way. And there's also a few other problems that I did put on your homework, which gives you a few more examples to look at, I suppose, or not. So is that good, Jordan? Or, okay. Whatty?
I caught somebody using his phone.
You caught someone using their phone? Mm-hmm. Oh. I forgot to warn you guys. He's the police. Let's see here. So you might find this solution. I doubt anybody here did this the way I did it. See, because I've learned something, that you can actually integrate absolute value, and the integral of absolute value is simply 1/2 x times absolute value of x. So if I know that, then I can straight up take the integral of this, right? Which is not something you probably learned in Calculus 1. I mean, at least I haven't taught it to my Calculus 1 except for like one semester. This is something I discovered relatively recently. So if I do that, I get this as my solution, which then if I fit the constant, I get 9/2 as it happens. So my solution is y is equal to x minus 3, absolute value of x minus 3 plus 9/2. Now, I don't really expect that you did it this way. I mean, if you did it, you should have done it in cases, right? You probably should have solved it in 2 cases and then glued those cases together, all right? And you'd end up with a solution. You might have ended up with a solution that looks more like this down here. These match up at 3, and it goes through 0 at the origin when put x equal to 0. So, and if you look at the quiz 1 solution from 2018 I'll post, you'll see how I derive the other way, all right? This is another integrating factor method problem. I think we've done enough integrating factor method today already, right? So there's another one. This one, there's another application, which is conservative forces, right? Every time we solve an exact equation, we're pretty much finding the potential energy for a force, right? That's almost true, but there's a minus sign difference, right? So if my force has the same coefficients here and here as this and that, right? The potential energy would be minus the gradient is equal to the force, right? So that means you're going to solve, and so I ignored my instructions here annoyingly, and I've just solved I found the level function, whose level curves are solutions to the differential equation directly. So I did the usual. I integrated both, and I think I combined answers or something. I get bored doing the integrating the exact.
Minutes.
How do I spell minutes? With an M. Let's see here. So here we're up against integrating dx over x squared plus 4. So I make a x equals 2 tangent substitution personally. Now you might have been taught to memorize this solution in Calc 2. If so, that's fine. I don't really expect you to show work necessarily for a Calc 2 integral, but I do expect you to be able to do them. This one here, there are various methods. I'm fond of the hyperbolic substitution. If I make a y equals tangent substitution, this ends up giving me just inverse hyperbolic tangent is the answer. There's another way to do this in terms of logs, because you can break this up into 1 over 1 plus y and 1 minus y with appropriate fractions, and then you'll get an answer that involves like a difference of logs of 1 plus or minus y. That's also fine as an answer. There's an identity which you can write inverse hyperbolic tangent in terms of logarithms. So they're not different answers really. Anyway, so that's my level. My solution here is that equal to a constant. But for a conservative force, you want minus the gradient. And so it's almost the same math, but instead of plus, we put minus, and that's the potential energy. So it's a twofer. Anytime you find the solution to an exact equation, you can easily write down the potential energy for a corresponding conservative force. And here's the silly details of that. So for the conservative force, you're solving partial u partial x equals minus p and partial u partial y equals to minus q. For the level equations, you're just solving f equal to partial x to b and partial f partial y equal to q, yes.
Can I use your phone?
Can you use my phone? Why? Oh, sure. There you go. Here. I thought you know how to do calculations.
No, not that high.
Not that high? This is a big number. All right.
You do so many apps on.
You can close them. All right, we talked about this one already. We do have some physics problems in here, but they're relatively, well, one-dimensional. It's kind of a pun. But so here we have MA equals to the net force. And again, recognize your enemy. This is a first-order linear differential equation in V, so integrating factor method. And the integrating factor is just an exponential. You multiply by it, reverse product rule, you got that. We have t times an exponential. We know how to integrate that from Calc 2. Noticing a theme? So we can do the integral by integration by parts, and there we go. So I've tried to make this homework include much Calc 2 nostalgia. We have seen integration by parts, we have seen partial fractions, we've seen trig substitution, right? I hope I've hit all the bases. Of course, you got your basic integrals. I'm hopeful that whatever I give you to integrate on the test, it won't be like super surprising, because hopefully you've reviewed a bit. All right. Because I know like some of these integrals we just don't end up doing in Calc 3, right? At least I don't usually try to work integration by parts into my Calc 3 examples. Calc 3 is enough evil for its day, you know? All right, so next up we had the eigenvector stuff and systems. And I've taken a more brief approach here than I have in class a lot. And it's simply this. So let me just kind of talk you through the method. I write down my characteristic equation. I figure out I have eigenvalues -2 and 5, right? So then next I have to write a minus -2 times I equal to the vector, times vector equal to 0. So that gives me a plus 2i, all right? Be careful here. This is usually where I make the mistake, is actually making this addition. So it might be good to not be like me, to actually write down a plus 2002 and like look at it and do this, all right? But there it is. I did it in my head, and I did it wrong, and then I whited it out and put it back in if you want to know the truth, all right? So there you go. But you should be like less sleepy than I was when I wrote this when you do your test, right? Okay, so when I look at this, I'm looking for a vector whose dot product with 3, 4 is 0. How do you make a vector perpendicular to a two-dimensional vector? All you do, take the components, switch them, and add a minus to 1. That'll make a perpendicular vector. So I don't need to write down UV equations or anything like that if I don't want to here. I can just see, by looking at this equation, the solution is minus 4, 3. Or that is a solution, right? I could also do minus 8, 6 if I wanted to be weird, right? Or whatever. I mean, there's like any multiple of this also works. For this one, subtract 5, I get minus 4, 4, 3, minus 3. How do I find a vector that when I take the dot product with this or that, I get 0? Well, I chose 1, 1. Of course, you could have put you could put 4, 4 there or 3, 3 there logically. That'd been fine too. There's always an ambiguity here, right? So the only way I could remove that ambiguity would be to do something like, demand that you normalize your eigenvectors to length 1. But I'm not going to do that because we haven't really talked much about that. Which is, by the way, a weakness of this semester. So sorry about that. I was trying to be, believe it or not, slightly kinder and gentler with the eigenvector stuff at the start of this course, because usually it comes at the end, towards the end of the course, so I'm a little bit more aggressive. But as I mentioned to you guys, the Monday, Wednesday, Friday time slot has messed up my usual testing division of material. And anyway, I much prefer to teach this class Tuesday, Thursday. It flows better. But anyway, we can't change that. So anyway, so I take e to the eigenvector plus c2 e to the eigenvector. That's all we need, right? Because it's a 2 by 2 system. This is the general solution. Any questions? Now, there was some. So this is the most unfair thing on the homework because I just slipped through the cracks. And if any of you had asked me any day about this in class, like I would have talked about it, but nobody did, so I didn't. How do you calculate e to the TA, right? That actually requires some kind of some thinking that we haven't done in class. I don't think, right? I don't think we have. But here's how I would do it. We know the magic formula, right? We know the magic formula. And so that allows us to, when we multiply the magic formula by an eigenvector, really special stuff happens, right? So we have like e to the TA times u1 is just e to the minus 2t u1, right? And likewise, e to the TA times u2 is e to the 5t u2 because they're eigenvectors, right? And basically this, when you multiply by an eigenvector, all of this stuff just collapses down to 0. And you're just left with I times the vector, which is just the vector. All right, so remember this. This is how matrix multiplication works. We talked about this in our discussion of the column by column solution stuff, remember? So if I have matrix times a vector, a matrix times a matrix where each column is listed like this, then there's this column by column rule. So this multiplies in there and in there. But this is that, and this is that. So I've got what I want. I want this, right? I've got this matrix, which I'm after, times this matrix, which I know, and just got numbers in it, by the way, and times this matrix of functions over here, right? So I can then solve for what I'm after by multiplying by the inverse matrix that we talked about here a little bit. Not a lot, but we did. So the 2 by 2 inverse, I just, and to inverse this, I AD minus BC, which gives me minus 7. I flip the diagonals, minus is on the off diagonals. That's my inverse. So I multiply the equation above on the right by the inverse, and that isolates the exponential, and it gives me, it's the product of this times that, which is this times that, which is that. It ain't pretty, but there it is. So that's probably the fastest way to calculate it here. But yeah. There is a way to derive that formula also from like a more systematic discussion of solution matrices. So like here's a theorem that I probably is in the book for sure, chapter 9. Probably, I don't know where, but I know it's in the book because most of the things I learned here I learned from the book. But here's the deal. If you have x and y fundamental solution matrices of, let's say, dr dt equals to AR, then you can write x is equal to a constant matrix times y for some constant invertible matrix C. And if you look at the calculation I just showed you to calculate the matrix exponential, that's really what I did. I showed that, and you could put the C on either side, all right? But, well, anyway, I don't want to go further into that at the moment. Let's go on here. That is a relatively minor point. So this next one here, we had a repeated eigenvalue of -2, right? Which means, well, as we saw, only one eigenvector, so that's not enough to find the general solution, right? So I have to go and solve the chain condition, as I did there. And that gave me a generalized eigenvector of order 2, all right? And then from the magic formula, I can derive the eigenvector solution, like the eigensolution here, and also the generalized eigensolution there, because the when I hit the u2 on this, it gives me a u1, and on this it gives me a u2, and u2 on this is just 0, as is the rest of it, as we've derived. So that's the solution in this case. That's what you have to work through. It's kind of funny. It would have been kinder if I had asked you to find the matrix exponential here, ironically, because if you use the magic formula directly, you might notice that this matrix, when you take the matrix and basically plug it into the characteristic equation, you get 0. So like it's easy to see this is 0. And if that's 0, then when you look at this series, everything drops out. The higher order terms drop out, and you're just left with this and this, which means there's your matrix exponential. So that, like if actually, it turns out when you only have one eigenvalue and they're repeated, the matrix exponential is actually kind of easy to calculate because of some calculation like this. And then this was a complex eigenvector problem. So I got lambda is 4 plus or minus 3i. And so here I made myself actually write out the a minus lambda I. See? And then the 4's cancel, but the minus 3i remains. And we're left with this. It's fairly evident that 3i times the first equation gets me the second equation, so I haven't made a mistake, yay. And I just look at this one, and I make a typo here, white it out, and then write down that v is equal to minus 3iu. I set u equal to 1. And then, getting straight to the point here, I have my real and imaginary components to the complex eigenvector, which we usually call a and b. That's what the book does in section 9.6, I believe. And so there you go. There's my complex exponential like that. My complex eigenvector over here. Multiply it out, real stuff, imaginary stuff, my solution 1, solution 2, and there's the general solution down there. Now, this one, we talked about how to do this last time. Here's the details. I won't bore you with them. It's not particularly, I mean, the answer is that. You can't do better than that because we're not given formulas for f, right? So the answer is integral. You'd actually prefer me not to give you formulas for f1 and f2, right? If I was to give a problem like this on the test, you definitely don't want to have formulas for f1 and f2, because if you have formulas for f1 and f2, then you could try to do the integrals, right?
Write down some rules of this class.
I need to write down some rules of this class?
No, I do.
Oh, you're gonna?
Can I?
Yeah, sure. There's a marker over there. So problem 23. Problem 23 is not like the others. Problem 23 is actually just back to basics. We have a system of differential equations. How do you solve it? Well, okay. Very good. No phone. Just when he writes things, there are other things he writes, so it's good. All right. I still got stuff to cover. So, so what I did for this one is I integrated the last equation. I got a constant. I plugged it into the next to last equation, and I integrated. Then I plugged that into the next to last equation, and then I integrated, and so forth, and so forth, and so forth, and so forth. And after a while of these integrations, you get to this set of solutions. So, yeah. And they should all have the same constants, and it should be such that every time I differentiate this, gets me to there, derivative of this gets me to that, and so forth, all the way on down to here after we differentiate that many times. Now finally, there's this problem here, which I will let you guys look at. The thing that was slightly tricky about it is that I put the things out of order a bit, so I'll let you look at that. I was going to talk about this today. Here's the answer. Thank you, Benjamin. So here is a plot of the potential energy, and these are energy level curves, right? So because for a conservative system, the kinetic energy plus the potential energy is equal to a constant, we must have that the the potential, the energy level has to be above the potential, right? If the energy level is below the potential, that means you've got negative kinetic energy, which is physically impossible and also mathematically questionable. And so then you can go from that and draw down here the graph in the so-called phase plane, something like that. This is a stable node. These are unstable nodes because, if you look at solutions coming into here, you might have some that are coming in, you have some that are going out. So if you were starting there and you were given a little nudge, you don't know which way you're going to go, right? Here, if you start here and you're given a little nudge, you're going to engage in some sort of like closed cycle around that point, right? So anyway, I'm sorry I have not devoted more class time to this. My bad. I do think if you watch those videos I sent you, they're pretty decent and poor planning on my part. Well, it could be, yeah. It was in the homework, so.